Take a look at this. That is GitHub Actions run that executed hopefully typical tasks anyone is executing every time a pull request is opened. It ran unit tests. It built a container image and pushed it to a registry. It updated manifest so that later on Argo CD or Flux can deploy the new release to production when that PR is merged to mainline. But before that happens, it created an ephemeral Kubernetes cluster and ran integration tests to confirm that everything works as expected. Now, I hope that's what everyone is doing, and if that's not the case, please let me know in the comments and I'll do my best to make a video about the whole process. But here it comes. There is one special part of that workflow run that I did not yet mention. There is something that hardly anyone does, yet something very important. That workflow run created a new database instance that should be used only and exclusively with that PR. To make it more interesting, that new database instance contains all the data we have in production, or when that is not a good option for security reasons, most of the data we have in production. As a result, those integration or any other types of tests, including manual ones, can be performed with full confidence that what we're testing is mostly the same as what is in production, at least when data is concerned. Now, that by itself is relatively easy to do as long as making bad decisions does not bother you. We could have connected that ephemeral environment to the production database and risk messing up data by changing schema or modifying real data. I doubt that anyone would do that. It would be silly to mess up production data for the sake of checking whether your commits are working as expected before they are even deployed to production. An alternative could be to have a separate production-like database with production-like data. Everyone can connect to that database, right? That's almost as silly as the previous option, since that results in constant clashes or constant delays. One developer would modify schema in a way that affects negatively the work of other developers. Some tests would introduce data that should not be there. Someone would delete data that is needed by other people working on the same project. Shared databases are a horrible idea, and the only solution is to give every developer and every ephemeral environment its own database. With that in mind, we could make a completely new database instance every time for every development environment and every ephemeral environment. In each of those, we could restore a backup of production data and, if needed, obfuscate confidential information. That would give us the safety of knowing that whatever we mess up is affecting only that new database instance, but not production and not other people working with us. That, however, comes with its own set of problems. First of all, creating a new database instance can take a few minutes. Now, you might think that a few minutes lost on each pull request is not a big deal, but if that's what you're thinking, I would agree. However, we should add to that time the time needed to restore a production backup and potentially obfuscate confidential information. That could be somehow streamlined as well. So now, if we did everything right, we lost around 10 minutes. That's not a big deal, right? That's not very tense though. Having a separate database instance that uses potentially significant amount of memory and CPU costs money by itself. Add to that the cost of storage where data is stored, and that's even more money. Now, multiply all that with the number of open pull requests and the cost keeps piling up. Once you're done calculating that, multiply it with the number of development environments, since apart from open pull requests, everyone should have their own database to work with, and the costs keep piling up. Soon you will go bankrupt, or you will revert back to the pain caused by everyone using the same database, both for development and the release process. All in all, running a separate database instance with separate data would be a way to go if it wouldn't be too slow and it would not cost too much. Ideally, all those databases would be ephemeral as well. They would exist only as long as they're needed to exist. They would also be serverless so that they waste CPU and memory only when used and shut down when not. Running serverless workloads is not anything new, even when that applies to stateful applications like databases. We could do something like that, right? There's more though. Data in the storage attached to those databases should be shared but any change to that data should not be applied to the main production or production-like database, but in a separate branch. We are already doing something like that with Git. There is mainline, typically production, and there are branches. Those branches are not copies, but references to the mainline branch that contains only the differences. That's how Git keeps being performant. However, we cannot use Git as database storage. It's not designed to do that. What we need, though, is to apply the same principle to database storage, right? Finally, all that needs to be fast. I expect creation of a new serverless database instance and a branch of production-like data to take seconds and not minutes or hours. Otherwise, execution of workload runs triggered by pull requests would take too long. Similarly, people would get very annoyed if it would take an hour to spin up a development environment every time we start working. For all I know, you might have chosen to watch this video mainly because you were bored while waiting for such an environment to spin up. Now, if we go back to the GitHub Actions workflow run we saw earlier, we can see that all those ideas are already implemented there. It took 5 seconds to create a new database instance that contains whole production or production-like data. It's a branch, so until I start changing the data, no extra storage is used. The database itself is serverless, meaning that it will run only when used and it will scale down to 0 replicas when not. As a result, memory and CPU are spent only when the database is used. All in all, it is fast, it uses memory and CPU only while being in use, and it uses storage only for the differences made on top of the existing data. It's the fastest and cheapest possible solution that allows everyone and everything to have a separate database instance, be it while developing or for ephemeral environments or anything else but production itself. Let me show you how I did all that. It's easy, as long as you know which tool or service to use. Here's what I did. I have a production database running somewhere. It could be AWS RDS, Azure Database for PostgreSQL, Google Cloud SQL, self-managed cloud native PostgreSQL, or anything else. It does not matter where my production database is. What matters is that I created a backup of it and restored it in Neon. Neon makes everything I will show you today possible. It is a serverless platform that separates compute and storage and branches data in a similar way we branch Git repositories. I rarely say something is awesome, especially early on in a video, but I will say it now. It's awesome. Let's take a look at the replica of production I made in Neon. First, I will use its CLI to get the connection string. Next, I will connect to it using pSQL and list all the tables I have over there. That is the database that contains the complete Lego inventory. Now, I hope you understand that I cannot show you my production data and allow you to copy it. That would get me fired, and I need my steady income so that I can keep making videos like this one for free. Lego database is decently big to be considered production size. It's not necessarily the biggest one out there, but it is big enough to show you how it all works and, more importantly, allow you to try it all out without using your own production data. The instructions how to reproduce what I'm doing are in the description over there, down, probably. Now, we can, for example, count the number of records in the Lego inventory parts table. There's over 500,000 records there. That's already a decent sized database that goes way beyond the silly demo I normally use. It can be considered a small, petite, tiny production. And here comes the interesting part. Just as with Git, we can list all the branches by executing neon control branches list. We can see that just as with Git, there is initially only the main branch, which happens to be the default. Here's my first complaint to Neon folks. Please make a consistent experience. Earlier outputs were giving me, by default, tables formatted as Markdown, while this one is giving me a proper table. That's inconsistent and as such confusing. Now, let's say that John would like to start working on a project locally. Among other things, John needs a database for his application, and to make his life easier, he needs it to have production-like data. John can simply create a new branch of the database just as he would create a new branch of the Git repo with the source code of the application he wants to work on. He could do that by executing neon control branches create and give it a unique name, just as one would give a branch a unique name. Boom! It took no time to create it. Right now he has effectively a new database with all the data he needs, while at the same time he did not have to create a new storage and duplicate all the data. Right now his database is using memory and CPU, but data is still the same. Let's confirm that the branch was indeed created correctly by listing all the branches. We can see that his branch is there and that it is ready to be used. Now, let's see whether it is indeed working. First, we'll retrieve the connection string pointing to the John Doe branch. Please note that we store the connection to the branch as neon_con_dev variable. From here on, whenever we use that variable, we'll be operating the database with the data from that branch, while neon_con without dev variable will continue being used to connect to the main branch. That way, you'll always know which one we're using at any given moment. Now we can retrieve all the tables from that new branch. There we go. We can see that the database has all the same tables as the original one, just as Git branch would have all the same files as the one it was taken from. We can confirm that further by retrieving the count of all the records in the Lego Teams table. Here comes the truly interesting part. Since that is a branch of data, we can do anything we want without risking pollution of the original data. For example, we can add a new record to the Lego Teams table. Now, let's retrieve the records count one more time. We have 615 records. That's one more than before. Okay, now let's do something more destructive, like drop of that table and take another look at all the tables in that database branch. It should not come as a surprise that Lego parts table is not there anymore. We just removed it. So far, everything John did was inside his own branch, which should not affect the main one. Let's confirm that's indeed true by connecting to the main branch and listing all the tables. There we go. We can see that Lego parts is still there, even though John dropped it from his own branch. The important note here is that those two branches still share most of the same data, so disk usage is still mostly the same. John's branch references the main one and only contains the differences. Now, let's say that John realized that he made a mistake and would like to revert his changes. That's easy as well. All he needs to do is instruct Neon to reset his branch, just as he would reset a branch in a Git repo. To confirm that the reset indeed worked, we'll list all the tables from John's branch again. There we go. We can see that the Lego parts table auto-magically reappeared, and John can continue working even though he is obviously too hasty, which might not be a bad thing. Unlike when using a shared database, he can easily experiment and move fast without wasting his time trying to figure out how his actions might affect others, which again is the same logic as using branches in Git. Finally, let's imagine that John is finished working. In that case, he would have two options at his disposal. One would be to do nothing. In that case, his database instance would become idle after a while and stop using CPU and memory. His data, on the other hand, would continue existing, but since Neon stores only diffs, that would be a relatively small amount, thus making it very inexpensive. The alternative would be to remove his branch, which is the option I like more, since I would assume that his experiments are stored as SQL code in whichever tool he uses to manage database schemas and transformations. In my case, that would be Atlas, which we'll see soon, but it could be anything else. In such a case, John can simply delete his branch. Let's confirm that's what really happened. We can see that his branch is gone, leaving us with only the main one. Now, let's see how we can incorporate database branches with application deployments to Kubernetes. Let's take a look at the relatively simple set of Kubernetes resources that we'll use to deploy an application to Kubernetes. First, we have a deployment like any other. The only thing that makes it special is the environment variable db_uri that assumes that the connection string to the database is stored in the secret silly demo. We'll get to that one later. Then we have a service and an ingress, which probably do not need any explanation to those having at least rudimentary understanding of Kubernetes. Finally, we have Atlas schema, It is a Kubernetes operator that manages database schemas, which happens to be the one I tend to use most. It also uses silly demo secret we commented on earlier to know how to connect to the database. More importantly, we have the schema SQL, which will ensure that tables, videos, and comments are in the database. If they're already there, it will make sure that they're identical, or it will create them if they aren't already there. Finally, since I was too lazy to create the schemas for the Lego tables we used earlier, I'll list them all as a way to exclude them from the tables managed by Atlas. As a side note, if you're not familiar with the Atlas operator, I strongly suggest watching that video over there, somewhere there, right? Just don't do it right away. Finish this video first, please. Now, let's say that Jane, John's coworker, would like to deploy her application with the database and double check whether the new additions to the schema are working correctly without disrupting anyone else. She already saw John working with branches, so she'll do the same by creating her own branch. This is my second complaint to Neon folks. Why didn't you create a Kubernetes operator? It would be so much better if Neon would be yet another resource deployed to Kubernetes instead of dealing with imperative CLI commands. With something like that, it could, for example, work with Argo CD or Flux. I know that I could wrap it all up into a Kubernetes job, but that's only the last resort. Please, please, please create a Kubernetes CRD and the controller. Next, she would get the connection string to her own database branch and create a secret we mentioned earlier. Now she can deploy her application that will be connected to her database branch. And that's it. Her application should be fully operational soon and connected to the database with schema changes she's working on applied with Atlas. And we can confirm all that by listing all resources, including ingresses, secrets, and Atlas schemas. Now, it may take a while until Atlas creates its own ephemeral database, figures out schema differences, and finally applies them to the branch we created with Neon. So, let's wait until that happens. Now we can confirm that the application is indeed connected to the Neon database branch we created earlier. We'll do that by sending 2 post requests that will instruct the app to insert data into the database, and a GET request that will retrieve that data. There we go, it worked. Now, to be on the safe side, let's list the tables in the DB branch. We can see that all the tables from the main branch are there, but also that we got 2 new tables created by the Atlas operator. Now, let's say that Jane is finished working. In that case, she would delete the whole namespace where the application is. This is the moment where it would be useful if Neon branch would have been created as a Kubernetes resource as well, since that would mean that there would be nothing left for Jane to do. That's, however, not the case, so she would have to remove the branch through the CLI. Now, to be clear, it would not be a big deal if she did not delete the branch, since the database would become idle after a while, thus not wasting any compute, and most of the data would not occupy any space on disk since it is a pointer to the main branch. I think that she could have even configured automatic deletion. Maybe, who knows. Still, I believe that it is a good practice to clean up everything that is not in use right away. Now that Jane is finished developing and she tested the changes through the application running in a local Kubernetes cluster and connected to her database branch, she can move forward and create a PR so that her changes to the code are merged to the mainline. Okay, let's see how we can integrate database branching into continuous integration. We'll use GitHub Actions for that, but the same principle would apply to any other workflow tool we might be using. Now, Jane should have switched to a new Git branch right away, but she didn't, she forgot. Still, there is no harm done. She can do it now. Next, we'll simulate some code changes by creating an empty file, mostly so that there is something we can push to the newly created branch. So, let's create a dummy file, add, commit, and push changes. Now we can create a pull request with the proposed changes to the code. That's where magic happens. That pull request, as any should do, triggered a GitHub Actions workflow run. Let's take a look at it. After a while, once the tasks are finished executing, the output should be as follows. That workflow run logged into container image registry, ran unit tests, built a container image as the new release, an updated Kubernetes manifest so that it can be deployed. That's pretty standard process so far. The new additions are the steps that follow. We deleted the existing branch just in case there was an update to the PR, in which case we might want to start over with a fresh database branch. Next, we created a new DB branch using Neon. From this moment onward, that branch contains all the data from the last production backup. Alternatively, we could have obfuscated confidential information or maybe had a subset of data if not everything is needed. It does not matter how we got what we have in the main database branch. What matters is that we created a new one so that the PR does not affect the main branch. And it took only a couple of seconds to do it. Brilliant, right? From there on, we executed the deploy up command, which created a new local kind cluster, applied ingress, created the namespace, created the secret with the URL through which we can connect to the database branch itself, and applied Atlas. That was the setup phase. Further on, that same command deployed the application, which, among other things, contains the Atlas schema with the changes to the database Jane proposed. Then we executed the integration test command, which, as the name suggests, run integration tests, which, among other things, verify that the changes to the database are working as expected. Once we got the confirmation through unit and integration tests that everything works as it should, we committed and pushed the changes to the Kubernetes manifest back to the Git repo. Once that PR is merged to the mainline, those changes to the manifest will trigger synchronization by Argo CD or Flux, and the release will be deployed to production. And that's it. The rest of the tasks that were executed are automated cleanups run by GitHub Actions automatically. So, here's how we did all that. I will let you explore that GitHub Actions workflow definition on your own actually. The only note I will give you to help out your exploration is that it uses DevOps to fetch all the tools it needs and that all the commands are written as no-shell scripts. Please check out those videos over there if you want to know more. They're there somewhere. And as always, links are in the description. Here's more good news. The database branch keeps existing. It's serverless. Soon it will become idle if no one is using it, but it will wake up if we start interacting with that same database. That way we can perform any additional validations we might want to run. We can confirm it's indeed still there by listing all the branches. We can see that the database branch silly_demo1 is there. Right now it is still ready, but it will soon scale down to 0 and become idle. Now, let's say that we did everything we need to do to ensure that Jane's release is ready for production and we can finally merge the PR into the mainline. That should have triggered yet another GitHub Actions workflow run, so let's take a look at it. Since we do not need the database branch anymore, that workflow deleted it. And we can confirm that by listing all the branches. The DB branch silly_demo1 is no more. It's gone. Poof. Here's how all that happened. That's a simple workflow with only one step that deleted the database branch. It's the same one we used in the other workflow, but this time it is not followed with the creation of a branch. And there's only one more thing I want to show before we discuss Neon pros and cons. For all of you who like pretty colors, there is a web UI as well. It has a bunch of features you might want to explore yourself. The only one I will show today is the view of the main branch. We can see that even the main branch is now idle. No one is using it, so it's scaled to 0 as well. There is no need to waste resources, which translates to money for anything that is not in use, including databases. Okay, now we can talk about pros and cons. Let me start by saying right away that Neon is fantastic. Treating databases as serverless is not something new, but when that is combined with treatment of data in a similar way as we treat Git branches, we get something very, very useful. Now, before we proceed, let me clarify the scenario I'm assuming before we discuss the pros and cons and see whether you should consider using Neon. Here it goes. I assume that production database is running somewhere other than Neon. That is not to say that you cannot or you shouldn't use Neon to run production, but only that I don't think that anyone should take lightly moving their production from AWS or Azure or Google Cloud or wherever that production database is. That would be a very tough decision. So, my scenario is that there is a production database somewhere, wherever that is, and that we create a backup of it. From there on, we might restore that backup into Neon's main branch as is, or we might obfuscate confidential data before we do that, or we might use only a subset of data. It doesn't matter. In any case, Neon's main branch is a full or partial copy of our production data. With that in mind, let's talk about pros and cons, starting with negative points. Actually, I don't have any significant cons to talk about. It truly works as advertised, and it is very useful. The cons that follow are all minor and could be considered my wish list rather than a list of real complaints. Number 1. Neon's outputs are very, very inconsistent, both in the CLI, the API, and the UI. For example, the CLI sometimes by default outputs data as a markdown table, while at others as a real table, whatever real table means. The same thing, whatever that thing is, might have 3 or 4 different names depending on whether we're using a CLI, reading the docs, or going through the UI. Error messages sometimes reference stuff that seem completely unrelated to what we're doing, often because we expect something with one name and got another. An example would be a message I got, an error message that said it could not apply config without read-write endpoint, which meant nothing to me until I realized that endpoints are the same as compute, which are 2 out of many different ways the same thing is called in Neon. It feels like different parts of the system were created by different people who never agreed what is what. It's not a big deal though. It doesn't take long to get used to such inconsistency, and if you get stuck, Neon folks are quick to help out. Still, it's inconsistent. Next, there are no Kubernetes CRDs and controllers. Kubernetes is not a novelty anymore, and I expected Neon to give me an operator so that I can manage branches in the same way I manage any other types of resources. It would be awesome if I could put Neon into a Helm chart or whatever else I might be using, together with the rest of the application components, just as, for example, I have CMPG or crossplane claims in there when working with databases in production. As it is not, I have to have a conditional that disables those when not running in production and execute CLI commands to get branches I need. Not a good thing, at least for those used to Kubernetes. What else? Third, the instructions for self-hosted version of Neon are just silly. We essentially need to compile it and run the binary directly. There is no container image, no Helm chart or anything similar. Or maybe there is, but it's buried somewhere deep in the docs where no one can find it. And my last complaint might sound silly to some, but I'll say it anyway. There are no Nix packages for Neon CLI. Nix is one of the biggest, and I repeat, biggest projects right now, and I don't remember the last time I could not find something as a Nix package. Until now. As you can see, there is no major downside, as far as I could discover. Some might call my cons nitpicking, while I would probably call it a non-essential wish list, except maybe for the self-managed setup. That one, depending on what you're doing, how you're doing, might or might not be an issue. Who knows? Okay, let's talk about pros next. I'll start by saying that it does what it's supposed to do. It works as advertised. It creates data branches so that disk usage is minimal, it is lightning fast, and database servers are serverless. That's all we really need for ephemeral environments. And that leads me to the next pro. Neon is unique. As far as I know, it's simplest, fastest, and the most cost-effective way to create replicas of databases for ephemeral environments. Now, to be clear, I'm not including Neon pricing into that statement. Pricings are hard to compare. What I'm saying is that it is very, very cost effective from the resource usage perspective. What else? Let's see. Okay, next, there are no gated features in the free plan, apart from limits to maximum CPU and RAM. Everything one would experience apart from support is available in the free plan. And that's awesome, since there are many companies that allow you to experience only a subset of features before opening your wallet. Okay, what's next? Oh yeah. The API and the CLI and the web UI are excellent. They are simple to pick up and do not leave anything to be desired. And finally, it is open source with Apache license, even though you might have trouble running it as open source. But it is open source and it is Apache license. That's all, folks. I think that Neon is great and that you should give it a try. Let me know what you think in the comments. Thank you for watching. See you in the next one. Cheers.